You'll see some of your homework problems are asking for what is the effective rate. So to find that, we have to talk about nominal and effective rates. So the annual rate of interest is sometimes called the nominal rate. So if they say that the interest is compounded 5% quarterly, that's your nominal rate. If the interest is compounded more than once a year, your effective rate of interest will be greater than your nominal rate. In other words, if you are paying interest on a loan and it's compounded more than once a year, you actually pay interest on your interest. So effectively, you pay a higher interest rate than the given nominal rate of interest. So here's an example of how to find the effective rate of interest. Suppose you are investing $1,000 at 5% compounded quarterly. The value of your money in t years is given by this formula with n equals 4, and t should be an exponent here. Now, if you rewrite the function as v equals 1,000 times, basically you pull out the t. So you're interested to see in this one, what's that number? So if you put it in your calculator, 1 plus 0.05 divided by 4 to the 4th power is 1.0509. So the growth factor, this looks like y equals c times a to the x. So this is your growth factor, 1.0509, which makes the growth rate 0.0509 or 5.09. This is the effective rate of interest, is 5.09. You see how it's slightly higher than what they say that the interest is, 5%? Okay? So that's how you find it. You're looking at just the portion 1 plus r over n to the n. And this will give you 1 point something, and that quantity after the point, that's your effective rate of interest. So if a sum of money is invested at 4% compounded monthly, what is the effective rate of interest? Well, it's going to be 1 plus the rate is 0.04. Compounded monthly means divided by 12, and then to the 12. So if you put that in your calculator, you'll get the effective rate of interest. So it's 1 plus 0.04 divided by 12 to the 12th power, and that to the 12th power, and then to the top. And it's 1.0407. So this makes the effective rate of interest equal to 4.07%, which is slightly higher than 4%. If a sum of money is invested at 3.5 compounded daily, this will be the effective rate of interest. 1 plus the rate is 0.035 daily divided by 365. Daily means n is 365 to the power 365. No. When you put that in the calculator, you get 1.0356. 1.0356. So that means that the effective rate of interest is this portion, so 3.56%, which is slightly higher than 3.5. All right, so the next type of problems is continuous growth. So basically continuous growth, we're looking when the compounding periods grow. So your n, if n is monthly, that means n is 12. If it's daily, it's 365. What if we let this compounding periods grow, like not just daily, maybe hourly or every minute? So this is where the number e arises. E is just like pi. Its value is approximately 2.71828, and then it goes on and doesn't repeat. So it arises naturally in cases of continuous growth at a specified rate. So if you let your x grow large, your x here plays the role of the n in the previous formula, this quantity is actually going to get closer to E. So if you let n or x be 10,000, let's see what happens. So this quantity, 1 plus 1 divided by 10,000, so, and then to the power 10,000. You see that it's 2.7181. If you let x be a million, it's just going to get closer and closer to this value, 2.71828, and that's E, your Euler constant. So then that's when the new formula comes into place. So if you are told that the value V of P dollar is compounded continuously, so this is the keyword you want to look for. So compounded continuously, basically you're changing that 1 plus 1 over n to the n power, you're changing that to BE, and this becomes the formula that you're going to use when you're told that the interest is compounded continuously. V equals P e to the RT, PERT, okay? Where P is your principal, R is the rate, and T is the time you're letting the principal stay in the account. So if you're investing 2,500, 4.25%, and you're asked to construct an equation that describes the value of your investment at year T, if your money is compounded continuously, as soon as you see continuously, you're going to write the formula V equals PERT. Okay? Every time. So then the value of your money, V, is going to be 2,500 because your principal is P, and it's 2,500 times E to the power, R is 4.25%, so it'll be 0.0425 times T. So this is the model. So the model has to have your input T and your output V. This is like Y and X here. Y for V and X for T. So this is the model. And now they're asking you, how much will your 2,500 be worth after 5 years? Well, after 5 years just means that T equals 5 in this equation. So let's put that in the calculator. So it's going to be 2,500 times E. E is right here on the division sign. So you have to press second division to get to E. And then to the power 0.0425 times T, which is 5 in our case. So you get 3092. So V equals $3092. So if you leave the money in the account for 5 years, it will become $3,092. Now, if your aunt plans to invest money for the same scenario as before, let's see how much you should invest if she gets 6% compounded continuously now. So continuously, that means write down the formula. It's V equals PERT, P-E to the RT. So now V is 50,000. And you don't know P, that's what you're going to solve for. And then E to the R is 0.06 and T is 18. So when you solve for P in here, P is going to be 50,000 divided by E to the 0.06 times 18. So 50,000 divided by E, second the division, to the power 0.06 times 18. 16,979 or 8, so 16,980. Okay, so if you look at the other two values, this is the smallest one. I think so, yes. So continuous compound is slightly better, but not that much better. Let's see what it was. It was 19,073 when it was compounded annually. When it was compounded monthly, it was 24. So when it's compounded continuously, it's almost 17,000. So it's slightly better. If money, for number 13, if money is invested at 6% compounded continuously, what is the effective rate of interest? So remember, to find the effective rate, you only looked at the portion without t. So basically the effective rate of interest is going to be e to the r. You're just looking at the portion without t. Let me remind you here, it's this portion without the t. Right? So if now you have v equals p to the rt, the portion without the t is e to the r. So e to the 0.06 because it's 6%. So when you put that in, it's 1.6183. 0.6183. So the effective rate of interest is 6.18. So it's slightly higher than the 6% that was reported. Alright, so every time you have a problem that says continuous interest continuously compounded, you use this formula, V equals P times E to the RT. It's not only money that can grow continuously, so other quantities can also grow continuously. And since these quantities don't represent principal and V, we're gonna call them something different. So this is the same formula, guys. Again, it's the same formula, but instead of V, we're using Y, and instead of P, we're using C, and instead of R, we're using K. So this formula, Y equals C times E to the KT, is for an amount that grows from the initial amount C. It grows continuously with continuous growth rate K. So again, I want to emphasize that this is the same as before. It's just that the quantities are not money now, so we call them differently. Okay? So this is what we call continuous growth and decay. And it is a growth when K is positive, and it is a decay when K is negative. Okay, so if we have 500 bacteria growing at a continuous rate of 3% per hour, the population of bacteria could be modeled by Y equals 500, that's your C, the initial amount of bacteria, times E to the 0.03, because the continuous rate is 3%, times T. Okay? So let's practice. Determine which of the functions below represents exponential growth and which one represents exponential decay, and then give the continuous growth and decay rates. So for this one, you notice that it is Y equals C times E to the KT, where K is 0.488, so it's positive, so this means it's growth, with growth rate K, it's this, right? So this is in decimal. To transform it into percentages, you move the decimal 2 places, so 48.8%. No, my pen. Okay, so growth, because K is positive, and then in percentages 48.8%. For number 15, you notice that K is negative now, so this is decay, and the decay rate K is moved decimal 2 places, so it'll be 1.4%. Next one, K is negative, so this is decay, and the decay rate K moved the decimal 2 places, so it'll be 0.9%. For this one, for number 17, K is positive, so this is growth, G, and then K is 2.5%. Now for number 18, we're asked to write the function that models the decay of a radioactive substance that is decaying continuously at a rate of 0.5% each year. So continuously, guys. So this means that I'm going to use this formula, y equals CE to the KT. So write the function. So y is going to be, I don't know how much it starts with, so I'm going to leave it as C. E, it says it's decaying, so K has to be negative, so I need to put negative 0.5%. I move the decimal to the left too, so it'll give me a 0.005 T. So this is the model, okay? Because it's decaying, K is negative, and then this percentage transformed into decimal. All right, let's move on to this last example. We are given that after T days, the amount of thorium-234, this is just the name of this element, in a sample is given by this. A of T equals 45 times e to the negative 0.029 T micrograms. How much was there initially? Well, this is right here. I start with 45 micrograms, right? Because this is the same formula, y equals c times e to the kt. Since it's decay, k is negative, and c, the initial amount, is 45. How much is there after 2 weeks? Well, after 2 weeks, what is t? Well, you have to be careful here. It says after t days, and they're asking how much is there after 2 weeks. So what is t in here? After 2 weeks, t means it's 14 days, because t is measured in days, not in weeks. So basically, I just need to plug in the amount after 14. So the amount after 14 is 45 times e to the negative 0.029 times t, right? T is 14. So when I put this in the calculator, 45 times e to the power negative 0.029 times 14 equals 29.98 micrograms. Sorry, my pen does not want to work. So after 14 days, which is 2 weeks, there are that many left. You start with 45 micrograms, and after 14 it goes down to 29.98, which makes sense because it's decay. But now this type of question might arise. What if we want to find out when there will be only half of the substance remaining? So let's think about this. What is this asking us? This is the formula we have. A to the t, a of t. So the amount after time t is, I start with 45 times e to the negative 0.029 times t. So they're asking us, when would there only be half of the substance remaining? So if I start with 25, I'm interested when this amount becomes half of 45, which is 22.5. So I know that the amount is 22.5. I know that I started with 45, And the question is, when does that happen? So I'm asked to solve for t. T is what? When. So what t? What is t such that this happens? So this is the reason why we're going to have to learn about logarithms. I don't know any algebra right now. If we don't learn about logs, I don't know how to solve for t. T is an exponent right here. I mean, I could divide by 45, so let's do that. So let's divide by 45, both sides. So then 22.5 divided by 45, that's 0.5, that's a half, equals e to the negative 0.029 times t, okay? So now I still have to solve for t, and t is an exponent, and regular algebra so far does not let us do that. So this is the reason why we have to learn about logarithms, because logarithms are going to allow us to solve for exponents. Yes. So before we learn about logarithms, we can graphically solve this problem. So let's use our calculator to solve this problem, and then we'll come back to it and use logarithms to solve it. So to use a graphical approach, basically I'm going to go to here and I'm going to graph this function, and then I'm going to graph this line. So in my y equals, I'm going to clear my things. So in y equals, I'm going to put the function e to the negative 0.029 times t. So it's going to be e to the power negative 0.029 times t. I don't have t, which is, we're using x in here, right? And then for my second function, I'm going to put 0.5, okay? And then I'm going to adjust my window. Let's graph it and see. If you hit graph and you can't see anything, then you need to think about how can I adjust my window. So I want my y, I want to see the 0.5 right here, right? Because 0.5 means that this is my y2 and this is my y1. So I want to be able to see this kind of in the middle. So then my y max should go up to 1.1, let's say. And then my x, so my x represents, what does x represent? It represents time, right? So we know that in 14 days, it goes down to 29.98. That's not quite half, right? 22.5. So let's go at least 2 more weeks. So let's put x min to go to 28. X max to go to 28. All right, so let's graph it and see. Okay, so this is my y1. It's the exponential decay right here. And then my y2 is the horizontal line. So when they are equal to each other, well, when they intersect, they're equal to each other. So this is your 0.5 and this is your e to the negative 0.029 times t. So to solve this, we set them equal to each other, right? So I need to find the intersection point, and that will give me the answer. So to find the intersection point, we go to second calc. So I press trace, and I'm gonna pick intersection. The first curve, I'm gonna pick the exponential decay curve, and the second curve, I'm gonna pick the horizontal line. And I press enter, and I press enter again, and that will give me that the intersection happens for x is 23.9. And remember, x is years. So when x is almost 24, the y is 0.5. So this tells me that t is 23.9. So t is 23.9 years. So days, sorry. So after almost 24 days, the amount of thorium is going to decay to half. So like I said, we're doing this graphically, but once we learn about logarithms, we're going to be able to do this algebraically using logs. All right, so that's it for today.